What if, what if everything you thought you knew about the universe was, just scratching the surface
Mm.
of a much, much stranger reality?
Mm.
What if our entire observable universe is actually inside a giant black hole?
It sounds like pure science fiction, doesn't it?
Yep,
Straight out of a movie.
exactly. But believe it or not, this isn't just some wild thought experiment. It's a highly speculative, yeah, but incredibly thought-provoking hypothesis.
Mm.
And it's been making waves, sparking some really intense discussions in the scientific community lately.
It truly is one of those ideas that sounds almost too fantastical to be true, yet it originates from genuine astronomical observations and, rigorous, even if preliminary scientific work. It really forces us to question assumptions we've held for decades.
Absolutely, and that's precisely what we're going to dive into today. Our mission really is to unpack this recent paper, the one suggesting our cosmos might not only be rotating, but maybe even nestled within a cosmic-sized black hole. So we'll explore the specific observations that ignited this build idea. We'll dig deep into the fundamental concepts, black holes, the universe itself, the things you need to grasp to even approach this.
The prerequisites, yeah.
Exactly, the prerequisites.
Hmm.
And then we'll critically examine why, despite its allure, the scientific community is, well, let's say, exercising extreme caution.
Healthy skepticism.
Healthy skepticism, exactly. So by the end of this deep dive, you should walk away with a richer understanding of galactic mechanics, those core cosmological principles guiding our view of the universe, and maybe most importantly, a clear sense of how scientific inquiry actually evolves through debate, through challenge.
To pushing the boundaries.
Okay, let's unpack this fascinating premise then.
Let's do it.
So let's start right at the beginning. Where did this mind-bending idea even come from?
Well, the catalyst for this whole deep dive is a specific paper. It's authored by Lior Shamir, who's a computer scientist at Kansas State University.
Okay, a computer scientist, interesting. Not an astronomer primarily.
Right, though he works extensively with astronomical data and algorithms. And look, this isn't some casual blog post or, an internet rumor floating around.
Right.
This research was published back in March in the monthly notices of the Royal Astronomical Society, MNRAS, as it's often called.
Ah, okay, MNRAS. That's
Yeah.
a big deal. That's a very well-regarded peer-reviewed journal,
Yeah.
right? With a huge history.
Exactly. Nearly 2 centuries old, prestigious. So it's a legitimate scientific claim. It's been put through a certain level of expert scrutiny, even if the conclusions are still very much up for debate.
That publication point is critical then. It means the work has been vetted, at least looked at seriously.
Yes. And the foundational data for Shamir's analysis, it comes from one of humanity's most, extraordinary scientific instruments, the James Webb Space Telescope, JWST.
JWST, of course. And it truly is revolutionary, isn't it? It's unveiled this unprecedented imaging power. It lets us capture incredibly fine details of things way out there in the deepest reaches of space.
And resolution is just stunning.
We're talking about seeing galaxies not just as fuzzy blobs, but with actual intricate structure, even at very high redshifts.
And redshift, just as a quick refresher for everyone listening, is basically how astronomers measure distance and speed for faraway objects.
Right, like the stretching of sound waves from a siren as it moves away, but with light.
Exactly. The further away something is and the faster it's receding due to cosmic expansion, the more its light gets stretched towards the red end of the spectrum. Higher redshift means further away and further back in time.
So when we talk high redshift with JWST, we're talking really early universe. Like that galaxy, JADIS GSZ 14-0, that was redshift, what, 14?
Around 14.2, yeah. Which
Okay.
means we're seeing light that left it just about 250 million years after the Big Bang, a quarter of a billion years.
Wow, that's incredibly early. Cosmic infancy, basically. A glimpse right back near the beginning.
It really is. And the specific data Shamir used for his study came from a particular JWST program, the Advanced Deep Extragalactic Survey, or JADES.
JADES.
Yeah, it's designed specifically as a deep field survey. Its whole purpose is to provide this incredibly detailed view of galaxies in the very early universe. And the patch of sky they looked at was called GOODS S.
GOODS S. And its location matters, you said?
It turns out it does, yeah. It's located relatively close to the southern galactic pole. So if you imagine looking down out of the plane of our Milky Way galaxy, that specific location becomes quite significant later on when we look at other observations.
Okay. So GOODS S, near the South Galactic Pole, observed by JADES using JWST. What did Shamir actually find in this data that sparked everything?
This is the core observation. He meticulously analyzed 263 spiral galaxies captured by JWST in this survey field. Spiral galaxies, like our own Milky Way.
Right.
And here's the truly puzzling part. Out of those 263, roughly two-thirds of them, 158 to be precise, were found to be rotating in the same clockwise direction as our Milky Way.
2/3 clockwise.
Yeah. While the remaining one-third, 105 galaxies, were spinning counterclockwise.
Huh. Okay, wait. Why is that puzzling? Shouldn't it just be random? 50-50.
Exactly. That's why it's perplexing. It seems to fly directly in the face of a core tenet of our standard cosmological model, something called the cosmological principle.
The cosmological principle, and I remember this.
Yeah.
It basically says the universe, on large enough scales, should look pretty much the same everywhere and in every direction. Isotropic.
That's the idea. Think of it like if you blow up a perfectly uniform balloon, any point on its surface looks pretty much identical to any other point, no matter which way you look. No preferred direction, no special spots.
So if the galaxy spins, that principle would predict.
A roughly even split, 50-50, half clockwise, half counterclockwise, wherever you look in the sky, assuming you look at a large enough sample.
This is a 60-40 split. Or more like 66-64, actually. That's not just a little bit off. That's a significant deviation from what you expect from pure chance, from that isotropic picture.
It really is. And the statistical significance here is, well, remarkably high. The probability of getting an asymmetry this strong, or even stronger just by random chance, it's incredibly low. About 0.0007.
0.000007.
Yeah. To put that in statistical terms, folks might hear, it's about 3.39 sigma.
3.39 sigma. That sounds significant.
Yeah.
Like really significant.
It is. Think of it like this. If you tossed a perfectly fair coin many times, getting a result this skewed would be like getting heads, say, 60% or more of the time. The odds of that happening by pure chance are less than 0.07%. It's so low that it really catches a scientist's eye. It yells, hey, look at me! Something interesting might be going on here.
So it's not just a minor blip in the data. It's a strong signal that seems to directly challenge one of the most fundamental assumptions we make about the universe. That's the kicker, isn't it? This seemingly simple observation could potentially unravel a cosmic cornerstone.
Precisely. It's a signal strong enough that you can't just ignore it, you have to investigate. And Shamir's initial claim, based on this observation, is that this imbalance, this preferred spin direction, could be a sign of a rotating universe.
A rotating universe.
And that's where the truly ambitious idea, the really mind-bending one, about our universe potentially being inside a black hole comes into play. Because, as we know,
Black holes spin.
black holes naturally rotate. So the thought process, the leap, is that maybe this large-scale cosmic rotation is imparting a preferred spin direction to everything within it, including entire galaxies.
Okay, wow. So the observed galactic spin imbalance might be evidence for a larger cosmic rotation, which might connect to black holes because they spin. But okay, hold on. To even entertain that truly audacious thought, our entire universe inside a black hole, we need to back up. We need to get on the same page about what these things even are. Let's nail out some prerequisites. Black holes. What are they, fundamentally?
Okay, basics first. At their core, black holes are regions of space-time where gravity is just so incredibly intense, so strong, that nothing can escape once it crosses a certain boundary. Not even light itself. They're like the ultimate cosmic prisons.
And what are their key defining features? What makes a black hole a black hole?
Well, there are a few key components. At the very center, theory predicts a singularity.
The singularity, the point of infinite density.
Exactly. A point where all the mass that fell into the black hole is crushed down to theoretically zero volume and infinite density. Though we should say our current physics, like general relativity, breaks down at singularity, so we don't fully understand what really happens there. It's a limit of our theories.
Right, and surrounding this singularity.
You have the event horizon. This is often described as an invisible one-way boundary. Think of it as the edge. Once anything matter, light, you name it, crosses this horizon going in, escape is impossible. It's the point of no return, the ultimate cosmic trapdoor.
Okay, singularity, event horizon, and the third key thing for this discussion.
Rotation. Black holes aren't static objects, they naturally rotate. This spin is a fundamental property. It's basically a remnant, a conservation of the angular momentum of the star or the cloud of gas that collapsed to form the black hole in the first place. Things in space tend to spin, and that spin doesn't just disappear when a black hole forms.
So they have a singularity, theoretically, an event horizon, the boundary, and they spin. Got it. Now, let's pivot to the universe itself. What's our standard picture, the prevailing cosmological model?
That would be the Big Bang Theory. Overwhelmingly the most successful model we have. It describes our universe as having originated from an extremely hot, incredibly dense state, roughly 13.8 billion years ago, and ever since then it's been expanding and cooling.
Okay, the Big Bang. Now, are there any conceptual similarities in the features of the universe described by the Big Bang model compared to the features of a black hole we just talked about? Because listening to the descriptions, it almost sounds, well, there are echoes maybe.
That's a really sharp observation, and it's precisely where this whole black hole universe idea gets its conceptual hooks in. Because, interestingly, yes, there are some striking conceptual parallels, at least on the surface.
Like what?
Well, the Big Bang Theory posits its own kind of singularity, the Big Bang singularity, also described conceptually as a point of infinite density and temperature at the very beginning.
Okay, so both have a singularity.
Conceptually, yes, but, and this is absolutely crucial, the Big Bang singularity is fundamentally different from a black hole singularity. It's not a physical location in space that everything is falling towards. It's better understood as a point in our past, the conceptual beginning of space-time itself, from which the entire observable universe expanded outwards. It wasn't an explosion in space, it was the beginning of space and time.
Okay, that's a critical distinction. A point in the past, not a point in space. What about a horizon for the universe? Do we have something like an event horizon?
We have something conceptually similar, yes, but again, different in its nature. We call it the cosmological horizon, or sometimes the particle horizon.
Cosmological horizon.
Right. It's not an event horizon in the sense of an inescapable boundary like a black hole's. It's not a physical wall out there. Instead, it represents the current limit of our observable universe. It's the maximum distance from which light, traveling at its finite speed since the Big Bang, could have possibly reached us today, given the age of the universe and its ongoing expansion. Light from beyond this horizon simply hasn't had enough time to get here yet.
So it's a limit to what we can see based on time and light speed, not a physical barrier you crash into.
Exactly. And of course, the other fundamental feature of our universe, based on vast amounts of observation, is that it's expanding. Galaxies are generally moving away from each other.
Okay, so let me see if I've got this. Both black holes and the universe in the Big Bang model have concepts of singularities and horizons. That is really interesting. It almost feels like the universe is echoing the structures it contains.
On the surface, these similarities are indeed too striking to ignore. And it's precisely why theoretical astrophysicists have been kicking around this idea in various forms for almost a century now. Ever since they realized black holes weren't just mathematical quirks in Einstein's equations, but could actually form in the real universe. The notion of our universe being trapped inside one gained conceptual traction because of these resemblances. You see singularity and horizon pop up in both descriptions, and your pattern-matching brain immediately goes,
But, as you hinted earlier, there's always a but in physics like this.
Hmm.
What are the crucial differences? The ones that really pose a significant problem for the simple idea that we literally live inside a standard black hole.
Yeah, this is where the appealing parallels start to break down, and the major problems for this hypothesis kick in. We already mentioned the difference in the nature of the singularities. One's a point in space, the other a point in time. But perhaps even more fundamentally, inside a typical black hole, everything space itself is flowing inexorably inward, crushing towards that central singularity. Everything is destined for collapse.
Right, falling in.
But our universe, by stark contrast, all observations show it's expanding. Galaxies are flying apart from each other, space itself is stretching. This fundamental difference in dynamics, inward crushing versus outward expansion, is a huge hurdle. It's a profound contradiction for the simple black hole universe idea, at least as we understand black holes through standard general relativity.
Okay, that makes sense. Contraction versus expansion. They seem fundamentally opposite. So how could anyone even begin to try to make a black hole look like our expanding universe? That sounds like it would require, I don't know, rewriting the rules of gravity or something. A pretty radical rethinking.
It absolutely is, and that's exactly what some theoretical approaches try to do. One avenue involves modifying the very equations of general relativity, Einstein's theory of gravity.
Modifying Einstein. Bold move.
Well, physicists do it all the time, exploring possibilities. One such modification is known as Einstein-Cartan theory. It's mathematically complex, but the gist is that it introduces an extra source of gravitational interaction related to the intrinsic angular momentum, or spin, of matter particles. This introduces something called torsion into the geometry of spacetime.
Torsion. Like twisting.
Sort of, yeah. You can think of it as a kind of intrinsic twist or rotation within space-time itself, separate from its curvature, which is what causes standard gravity. In Einstein-Cartan theory, this torsion acts as a kind of repulsive force at extremely high densities. And crucially, this repulsive force could potentially prevent the formation of singularities inside black holes altogether.
Ah, okay, so instead of collapsing to infinity, the matter bounces back somehow.
In a way, yes. And this is where it connects back to the black hole universe idea. In some interpretations of this modified theory, a black hole, instead of having that infinitely dense singularity at its core, might become a theoretical bridge, a connection point to something called a white hole.
A white hole? Okay, I've heard of these. They're like the opposite of black holes.
Exactly. Think of a white hole as the bizarro time-reverse twin of a black hole. While a black hole is a region you can enter but never leave, a white hole is a hypothetical region of space-time that cannot be entered from the outside and is forever spewing out its contents, matter, energy, light, into its surrounding universe.
Spewing stuff out. Okay, I can see where this is going.
Right. The tantalizing, though highly speculative, idea is maybe our expanding universe is that spewing out part. Maybe it's the exit of a white hole, which itself was formed from the collapse of matter into a black hole in some other parent cosmos.
Wow. That's quite a conceptual leap. Truly pushing the boundaries. But if white holes are possible in these theories, why don't we see them? Or evidence of them? What's the catch?
The big catch, the major problem with white holes, even in these modified theories, is their predicted catastrophic instability.
Unstable. How so?
Well, while they exert gravity like anything else, matter can never actually enter them from the outside. So, theory suggests that as soon as even a tiny speck of dust or even a single photon approaches a white hole from the outside, the interaction causes the whole thing to collapse instantly. The energy runs amok, and boom, it converts immediately and violently into a regular black hole.
So they basically can't exist for any length of time. They just vanish.
Pretty much. This extreme instability is a significant reason why most physicists don't think white holes actually exist in our universe. They simply couldn't stick around long enough to be observed, let alone sustain an entire cosmos like ours expanding from within one.
So the maybe scenario here relies on a whole chain of speculative steps. Modify gravity, avoid the singularity, form a white hole bridge, and somehow make that white hole stable enough to become our expanding universe.
Exactly. It's a tantalizing thought, for sure. It offers this potentially neat package explaining cosmic expansion, maybe connecting to rotation, even hinting at a multiverse if our universe came from a black hole in another one. But you're right, it requires many maybes and significant theoretical gymnastics to make it work.
Like, how do you get an expanding, seemingly flat universe out of something that's supposed to be a region of intensely curved space-time?
Good question. Maybe there's some exotic mechanism we haven't thought of that makes them appear flat or expanding once they reach cosmological scales. The maybes just keep piling up. And critically, this whole white hole universe idea, while fascinating conceptually, currently has zero solid supporting observational evidence.
Right. It's theory, but the observations don't point that way.
Exactly. While the universe has certainly thrown curveballs at us before, and sometimes theory does lead observation, the current body of evidence just doesn't lead us in this direction at all. The theoretical challenges are immense, the instability problem is severe, and there's a complete lack of direct observational support. So while it's a fun concept for theorists to play with, it remains highly speculative, very far from being a mainstream cosmological model.
Okay, that's a helpful grounding. The concept is out there, it has these interesting parallels, but it's built on shaky theoretical foundations and lacks observational backing right now. Let's shift our focus back then to the concrete observations that started this whole discussion, the nitty-gritty of Shamir's actual findings with JWST. How exactly did he go about collecting and analyzing this data to identify that galaxy spin imbalance? What was his precise method?
Right, back to the data. So the data he used, as we said, came from the Goods S field, part of the JD's survey. The images were mainly captured using JWST's near-infrared camera and ARCam using specific filters infrared wavelengths of 0.9, 1.4, and 2.0 micrometers.
Why those specific infrared bands?
They're particularly good for seeing distant galaxies. The light from these early galaxies is significantly redshifted, meaning its wavelength is stretched, often moving ultraviolet and visible light into the infrared part of the spectrum where JWST excels. These bands allow astronomers to cut through dust and see the structure of these very distant objects clearly. And the specific field, Goods S, covers a known patch of sky near the southern galactic pole, defined by specific right ascension and declination coordinates.
Okay, so he had these incredibly detailed, deep infrared images from JWST. But the crucial next step, how do you actually determine which way a spiral galaxy is spinning? Especially when they're just tiny specks of light from billions of light years away. Can you just look at them and tell?
That's a really important question, and it highlights a major challenge in this kind of research. Simply looking at an image and making a judgment call manual annotation can be very subjective.
How so? Wouldn't the spiral arms make it obvious?
You'd think so, but it can be surprisingly ambiguous, especially for faint, distant, or oddly oriented galaxies. Different human annotators might look at the same fuzzy image and have different opinions on the curvature of the arms or the overall rotation. Plus, humans can have unconscious biases.
Biases, like preferring one direction.
Exactly. In fact, in earlier citizen science projects, like the famous Galaxy Zoo, where hundreds of thousands of volunteers classified galaxies by eye.
Oh yeah, I remember Galaxy Zoo. That was huge.
It was fantastic for engaging the public. But analyses showed there were actually substantial degrees of errors because volunteers often disagreed, and more significantly, there was a documented human bias. People tended to classify a slightly more galaxies as rotating counterclockwise than clockwise, even when shown mirrored images that should have canceled out any real cosmic preference.
Huh. A counterclockwise bias. Weird.
It is weird, but it was a measurable effect. So relying solely on human judgment, especially for subtle effects or large statistical studies, is generally not considered a robust, objective scientific methodology. It's too prone to subjectivity and bias.
Okay, so manual checking might be useful for verification, but for the main analysis, Shamir needed something automated, something objective. What did he use?
He used a specific computer algorithm called Ganalyzer. It's actually an algorithm he developed himself and has refined over several previous studies using data from Hubble, SDSS, and Pan-STARRS before applying it to JWST.
Ganalyzer. Okay, how does it work? What does the computer see?
It's quite clever. It performs several steps automatically. First, it has to identify the galaxy itself, separating it from the background noise and other foreground stars or objects in the image.
Right, isolate the target.
Then, once it has the pixels belonging to the galaxy, it transforms the image. It essentially unrolls the spiral galaxy into a flat, two-dimensional map. Imagine taking the galaxy image and plotting its brightness, intensity, based on the distance from the center and the angle around that center. This creates something called a radial intensity plot, which is stored as a matrix, specifically a 35 by 360 matrix in this case.
Okay, like a polar coordinate map of brightness, 360 degrees around, and 35 steps out from the center.
Exactly like that. And the key insight is that the spiral arms of a galaxy are typically brighter than the regions between the arms at the same distance from the galaxy center.
Ah, because there are more stars concentrated in the arms?
Precisely. So the Ganalyzer algorithm looks for these brighter regions in that unrolled map. It uses a peak detection algorithm on each radial line, each distance step, in that plot to identify the pixels that likely belong to the spiral arms, the bright ridges on the map.
Okay, it finds the arms.
Yeah.
Then how does it get the spin direction from that?
Once it has identified a collection of these arm pixels, it applies a mathematical technique called linear regression. Basically, it tries to find the best fit straight line through the positions of these bright arm peaks on the unrolled map. The slope of that best fit line tells you how the arms are curved. And the sign of that slope, whether it's positive or negative, definitively determines the direction towards which the arms of the galaxy are curved. That gives you the rotation direction, clockwise or counterclockwise.
Clever. Using the overall curve of the identified arms. But are spiral arms always a reliable indicator of the galaxy's actual rotation direction? Are there exceptions where the arms seem to go the wrong way?
That's a fair question. Overwhelmingly, yes, the direction of spiral arms is a very reliable proxy for the direction of stellar rotation. Specifically, we look at whether the arms are trailing.
Trailing, meaning they lag behind the rotation.
Exactly, like the wake behind a boat. The vast majority of spiral galaxies observed show trailing arms. Studies going way back to the 1950s, using different methods like analyzing galaxy spectra or looking at how dust lanes silhouette the arms, have confirmed this. It seems to be the natural state. Now, are there exceptions? Yes, but they are extremely rare. The most famous example is a peculiar galaxy called NGC 4622, which actually has prominent leading arms that seem to point in the direction of rotation.
Leading arms?
Yeah, it's a very unusual, well-studied oddball. But for the vast majority of spiral galaxies, assuming trailing arms gives you the correct rotation direction. So, The method used by Ganalyzer is considered sound for statistical studies like this.
Okay, so the algorithm finds the arms, fits their curve, determines the direction. But one more check. How did Shamir make sure his own algorithm wasn't somehow biased? That it wasn't accidentally favoring clockwise or counterclockwise results?
That's a critical validation step for any automated analysis, especially when you're looking for a subtle asymmetry. To prove the algorithm itself was impartial, Shamir performed a crucial test. He took the entire Goodsess field image from JWST and digitally created a perfect mirror image of it.
Flipped it horizontally.
Exactly. Then he ran the exact same Ganalyzer algorithm on this mirrored image. If the algorithm had any inherent bias towards, say, clockwise patterns, you might expect the results from the mirrored image to be skewed or inconsistent.
And what happened?
The results were perfectly inverse. The galaxies identified as clockwise in the original image were identified as counterclockwise in the mirrored image, and vice versa with the exact same numbers. This unequivocally confirmed that the algorithm itself is symmetrical and doesn't introduce its own directional bias.
That's reassuring. Did the algorithm also filter out problematic galaxies?
Yes, it has built-in filters to improve reliability. For instance, it's designed to primarily analyze spiral galaxies, so it automatically tries to filter out elliptical galaxies, which don't typically have defined spiral arms or clear large-scale rotation in the same way. It also filters out galaxies where the rotation signal is too weak or ambiguous, for example. If it finds fewer than 30 significant arm peaks, or if the calculated slope of the arms is very flat, less than 0.35, it simply doesn't assign a direction, avoiding uncertain cases.
Okay, so it's a carefully designed, validated, and filtered process. After applying all this to the JWST data from Goods-S, what were the final definitive numbers?
After running Danalyzer on the JWST data and applying these filters, the algorithm identified 263 galaxies with a clearly measurable direction of rotation. Out of these 263, 105 were rotating counterclockwise and 158 were rotating clockwise.
105 counterclockwise, 158 clockwise. That's the roughly two-thirds, one-third split again?
Exactly. And as we calculated earlier, assuming a purely random 50-50 distribution is the null hypothesis, the probability of observing an imbalance this large or larger just by chance is that incredibly low, 0.0007, the 3.39 sigma significance level.
That's a really strong statistical signal suggesting it's not random chance. Can you actually see this difference if you just look at the images Shamir analyzed?
Well, the algorithm provides the quantitative objective measurement. But yes, Shamir notes that visual inspection of the galaxies the algorithm flagged generally shows consistency. A human eye looking at the images tends to agree with the direction the algorithm assigned. The asymmetry isn't caused by lots of individual galaxies being misclassified. It seems to be a genuine imbalance in the overall population within that field.
Now, here's something interesting you mentioned earlier.
Yeah.
This isn't the absolute first time astronomers have noticed hints of an unequal number of galaxies spinning in opposite directions. Right? This JWST result isn't coming completely out of the blue.
You're absolutely right. While JWST's power lets us probe much deeper and earlier in the universe with stunning clarity, this phenomenon and asymmetry in galaxy spins has actually been hinted at and even observed to some degree in data from previous generations of telescopes. We're talking Earth-based surveys like the Sloan Digital Sky Survey, SDSS, and Pan-STARRS, and also earlier observations with the Hubble Space Telescope. Some papers discussing potential asymmetries go as far back as the 1980s.
The 80s, wow, so this has been lingering for a while.
It has. Shamir's recent work, especially with the high-quality JWST data, is significant because it seems to provide much stronger statistical evidence and extends the observation to much higher redshifts, but it definitely builds upon a historical thread of similar, albeit often less statistically powerful, findings or suggestions from earlier datasets.
So it's not an entirely isolated observation. Is there a consistent pattern seen across these different studies and datasets? Does that strengthen the JWST finding?
Yes, and this is a crucial point Shamir emphasizes. Several previous studies using data from SDSS, Pan-STARRS, and Hubble indicated that the difference between the number of galaxies rotating clockwise versus counterclockwise appears to increase as you look at higher redshifts.
So the asymmetry gets stronger the further back in time and space you look.
That seems to be the trend suggested by the earlier data. And the magnitude of the asymmetry Shamir found with JWST in the very early universe, high redshift, is indeed stronger than what was typically seen in those previous lower redshift surveys using ground-based telescopes, or Hubble. This fits perfectly, Shamir argues, with that previously observed trend. He provides data, for example, in a 2020 paper, showing this trend clearly across different redshift bins in SDSS data.
That's really fascinating. The potential cosmic pattern that's been present since the early universe and perhaps becomes more pronounced over time or with distance. What about the location in the sky? You mentioned goods less being near the galactic pole was important. Does that fit with earlier findings too?
It absolutely does. And this is another key piece of evidence supporting the idea that this isn't just random noise. Earlier, large-scale surveys, particularly the DA's Legacy Survey, which mapped over 1.3 million galaxies across a huge area of the sky, showed evidence for a higher degree of spin asymmetry when looking specifically towards the galactic poles.
So looking straight up or down out of the flat disk of our Milky Way.
Exactly. And the Good S field, the patch of sky Shamir studied with JWST, happens to be located relatively close to the southern galactic pole. So the strong asymmetry found there aligns beautifully with where previous surveys suggested the asymmetry might be strongest.
And what about JWST observations in other parts of the sky, not near the poles?
That's another crucial check. JWST's very first spectacular deep field image, remember that one? Webb's first deep field, SMSES 0723. That field is not located near a galactic pole.
Yeah.
And when Shamir analyzed the spiral galaxies in that field using the same Ganalizer method, he found essentially no statistically significant asymmetry at all. It was a near-perfect split. 21 galaxies rotating counterclockwise, 19 rotating clockwise. Basically 50-50, exactly what you'd expect from random chance if there's no large-scale preferred direction in that part of the sky.
Wow. Okay, so the asymmetry seems stronger near the poles and weaker or non-existent away from the poles, even with JWST data. That really strengthens the case that something directional is going on tied to our position or the large-scale structure, doesn't it?
It certainly makes the pattern look much more systematic and less like a random fluke in one particular data set. The consistency across different telescopes, different eras, different redshifts, and specific locations in the sky, especially the pole alignment, builds a more compelling, though still debated, case for a genuine cosmic asymmetry.
Okay, so the evidence for some kind of asymmetry seems to be mounting, especially with JWST confirming and strengthening these earlier hints. But naturally, finding this potentially revolutionary challenging the cosmological principle is going to face intense scrutiny. And it has. The scientific community thrives on skepticism, on poking holes in new claims. So let's get into that. How does Shamir address the counter-arguments, the studies that did claim to find a purely random distribution of galaxy spins? He seems to actively rebut many of them, right? Arguing their methods were flawed or their data, when looked at differently, actually supports his view. This back and forth is really how science progresses, isn't it? Critiquing methods, reanalyzing data.
Absolutely. Shamir's papers aren't just about presenting his JWST results in isolation. They're often comprehensive reviews of the existing literature, where he systematically goes through previous studies that claimed randomness and points out where he believes their methodologies fell short, or how their results, when interpreted correctly or combined with other data, actually fit into the larger picture of non-randomness he's proposing. It's a classic example of scientific debate playing out in the peer-reviewed literature.
Okay, let's break down some of those specific rebuttals. What about some of the really early studies that suggested randomness? You mentioned one from the 90s.
Yeah, for example, a study by Ai and Shugai in 1991, they did find a very close split, 3,257 clockwise versus 3,268 counterclockwise galaxies. Looks pretty random, right?
It seems like it, yeah. Almost perfectly 50-50.
But Shamir points out two key issues. First, they relied on manual annotation, which we've already discussed has subjectivity problems. Second, and perhaps more importantly, their dataset was just far too small, especially considering the relatively low redshift of the galaxies they could observe back then. With only about 600 to 500 galaxies in total, he argues, the statistical power was insufficient to detect the kind of subtle asymmetry seen in larger, deeper surveys. So the result wasn't necessarily proof of randomness, it was just statistically consistent with randomness because the sample wasn't large or deep enough to reveal the potential underlying asymmetry. It didn't conflict with non-randomness, it just couldn't confirm it.
Okay, sample size matters. What about the big one, Galaxy Zoo? Land et al., 2008. That used hundreds of thousands of classifications from volunteers. Surely that data set was large enough.
It was certainly large in terms of the number of classifications performed, but as we touched on earlier, it had that significant, well-documented drawback. The human bias towards classifying galaxies as counterclockwise, this extreme bias of approximately 15%, as Shamir describes it, completely swamped any potential real cosmic signal in their initial super clean dataset. You just couldn't tell if the excess of counterclockwise galaxies was real or just humans seeing things.
Right, the counterclockwise bias. Did they try to fix that?
They did. After the bias was identified, they ran a specific sub-experiment where volunteers classified both original galaxy images and their digitally mirrored counterparts. This allowed them to statistically correct for the human bias.
Ah, clever. And what did that de-biased dataset show?
The de-biased dataset was much smaller. Only about 11,000 galaxies were analyzed this way because the bias was caught late. And the result from this smaller, de-biased sample showed only what Shamir calls marginal statistical significance, an asymmetry of about 1.5% to 2.2% favoring counterclockwise rotation. On its own, maybe not slam dunk evidence, however, Shamir argues that even this marginal result, when combined statistically with other independent datasets, like from SDSS, pushes the overall significance for a non-random distribution much higher, effectively supporting his broader claim rather than refuting it.
Okay, so the raw Galaxy Zoo data was biased, and the de-biased part, while small, hinted at the same direction of asymmetry. What about studies that used automated methods, computers, to avoid human bias, but still claim to find randomness? Like Hayes et al. In 2017.
Right. Hayes et al. Used automation, specifically machine learning, to classify spiral galaxies. And interestingly, in parts of their analysis, they also initially found an excess of counterclockwise galaxies, which actually aligns with Shamir's findings from other datasets like SDSS.
So why did they conclude randomness then?
The specific experiment in their paper that yielded a random distribution was one where they used machine learning not just to classify spin, but also to select which galaxies were spiral in the first place. And here's Shamir's key criticism. He points out that the researchers explicitly state in their paper that they manually removed specific features from their machine learning analysis, and guess what features they removed? The very features that are known to correlate with the direction of rotation of the galaxies. They specifically chose attributes that were disjoint with those that Shamir found to be correlated with chirality, handedness, or spin direction, and deliberately removed chirality information.
Wait, so if I'm understanding this right, they used a machine learning tool to look for spin patterns, but first they told the tool to ignore the very features that indicate spin direction. That sounds completely backwards if you're actually trying to find a spin asymmetry.
That's precisely Shamir's argument. He contends that if you deliberately remove the information that allows you to determine spin direction, you will naturally weaken any signal of unequal number of galaxies that rotate in opposite direction, potentially making a real asymmetry disappear. It's like trying to see if there are more red cars than blue cars, but first making all the cars gray.
Okay. Did Shamir test this?
He did. He says he reproduced the Hayes et al. Experiment using the exact same publicly available code and data, but he ran it without manually removing those crucial spin-related features. And when he did that, his reproduction showed a clear, statistically significant asymmetry, consistent with the asymmetry seen in SDSS and other surveys. He argues this demonstrates that the original conclusion of randomness by Hayes et al. Was likely an artifact of their specific choice to exclude relevant features.
That's a pretty strong rebuttal.
Okay.
Moving on to even more recent methods, deep neural networks, like Tadaki et al. In 2020, using data from the Hypersuprime survey in Hawaii.
Yes. Tadaki et al. Used deep learning for automatic annotation on a very large data set from HSC. They found 38,718 galaxies rotating clockwise and 37,917 rotating counterclockwise.
Okay, so slightly more clockwise.
Slightly more, yes. And if you just do a simple statistical test, binomial distribution, the probability of getting that difference by chance is about 0.00019. That's statistically significant.
So that supports asymmetry then?
Well, Shamir argues it does. Firstly, the result is statistically significant. Secondly, the fact that they found a slight clockwise excess actually agrees with the location of the HCS footprint, which is predominantly in the northern hemisphere, closer to the northern galactic pole. Shamir's own work suggests the asymmetry might flip direction between the north and south poles, a dipole pattern, so finding a clockwise excess in the north could fit the overall picture where he found a clockwise excess near the south pole with JWST.
Ah, so the direction of the asymmetry might depend on which pole you're looking towards.
Mm-hmm.
Interesting. But I recall reading that Tadaki et al. Themselves were cautious about claiming proof of asymmetry from their result. Why was that?
Their caution stemmed from the known error rate of the deep neural network they used. While the network was quite accurate overall, they noted that the uncertainty or error margin in its classifications was numerically larger than the small asymmetry they observed, the difference between clockwise and counterclockwise counts. So they couldn't definitively rule out that the observed difference was just due to classification errors by the AI.
Okay, so the signal might have been real, but it was smaller than the noise or uncertainty in their measurement.
Exactly. So while Tadaki et al. Couldn't consider it soundproof on its own, Shamir argues their result is clearly in agreement with the other previous reports that show an unequal number of galaxies that rotate in opposite directions, and it certainly doesn't conflict with those findings. If anything, he suggests, it lends further credence to the overall pattern, especially the potential north-south difference.
Makes sense. What about other recent neural network studies? There was one by Jia, Zhu, and Penn in 2023 using both SDSS and the newer DSI legacy survey data.
Right. They also used deep neural networks and looked at different accuracy thresholds for their classifiers. Using SDSS data, which covers mainly the northern hemisphere, they found 9,218 clockwise and 9,442 counterclockwise galaxies.
So slightly more counterclockwise there.
Yes, an asymmetry of about 2.4% with a p-value, the probability of it being chance, of about 0.05.
Key 0.05. That's borderline statistical significance, usually the threshold scientists use.
It is borderline, but technically significant by the common standard. Shamir highlights that this result agrees with the asymmetry shown in Shamir 2020, which used a larger sample from the same SDSS survey and found a stronger signal in the same direction, counterclockwise excess in the north. So again, he argues it's consistent, even if weaker, due to the smaller sample size analyzed by Jia et al. In that specific test. It's definitely not in conflict with the other observations.
And what about their analysis of the DII legacy survey data? That survey covers a huge area, right? Both northern and southern skies.
Exactly. DALS has a massive footprint, covering large parts of both celestial hemispheres. This actually makes predicting an overall asymmetry tricky, because if there's a dipole pattern, say counterclockwise excess in the north and clockwise excess in the south, looking at both hemispheres combined could cause the signals to partially cancel each other out.
Okay.
Yeah.
So what do they find in DSI?
They found 11,649 clockwise and 11,919 counterclockwise galaxies. Again, a slight counterclockwise excess overall. The p-value for this difference occurring by chance was about 0.04.
P0.04. Also statistically significant. Just barely.
Right. So Shamir's take is that even with this huge hemisphere-spanning survey where you might expect cancellation effects, they still found a statistically significant asymmetry. He concludes that this result also does not conflict with the contention that the distribution is not random, and if anything, further hints at a complex, large-scale pattern rather than pure randomness.
Okay, and another study address. Now, there was also a claim, I think, by I et al., again in 2021, suggesting that some of the earlier asymmetry findings might have been caused by simply having duplicate objects in the data sets, like counting the same galaxy twice somehow?
Yes, that claim was made specifically aimed at some of Shamir's earlier work with SDSS data. I et al. Suggested that using a particular SDSS catalog could lead to duplicate entries, which might artificially inflate the statistical significance of any observed asymmetry.
Yeah, how does Shamir respond to that? Sounds like a potentially serious data issue.
He refuted it quite strongly. First, he pointed out that the specific catalog I et al. Were criticizing was one he had used in a 2017 paper for a different purpose photometric analysis, measuring brightness and color, not for analyzing spin direction asymmetry. He made no claims about a dipole axis based on that specific dataset in the way I et al. Implied. More importantly, Shamir stated that when he attempted to reproduce I et al.'s own analysis, using their exact same data and method described in their 2021 paper, he obtained different results. Specifically, he did find a statistically significant non-random distribution, contradicting their claim of finding randomness due to duplicates. This suggests, he argues, an error in the reproduction or analysis.
So he claims their attempt to show duplicates caused the signal was itself flawed.
Yes, and he also critiqued their explanation for why their results differed from his earlier findings. He argued their explanation relied on an incorrect assumption that the SDSS sample was uniform, when in reality SDSS covers only part of a hemisphere and the density of observed galaxies varies significantly across the survey area, which needs to be accounted for properly.
Okay, quite a technical back and forth there. Finally, what about the most recent challenge mentioned in the paper from Patel and Jesman in 2024? They proposed a new complex ad hoc statistical method to reevaluate the asymmetry claims.
This is a major point of contention for Shamir, and he dedicates significant space to rebutting it. His primary and quite damning critique is that he believes the new statistical method proposed by Patel and Desmond is fundamentally incapable of detecting the kind of asymmetry being discussed. He claims it does not respond to asymmetry in the distribution of galaxy spin directions at all.
How does he demonstrate that?
He performed a simulation. He created synthetic datasets where he deliberately engineered an extremely asymmetric distribution of galaxy spin directions data, where a large, undeniable asymmetry was built in from the start. Then he applied the Patel and Desmond statistical method to this deliberately skewed synthetic data.
Now the result.
According to Shamir, the method still reported a random distribution. It yielded a non-significant p-value, around 0.25, failing to detect the strong asymmetry that was known to be present in the input data.
Wow. So if his simulations is correct, their test wouldn't find asymmetry even if it was staring it in the face.
That's Shamir's conclusion, yes. He argues this shows their method is simply not sensitive to the type of asymmetry being investigated, making their conclusions based on it invalid. Furthermore, he also states that Patel and Desmond's paper attempted to reproduce some of his own previous results using his methods, but that their reproduction provided different results than the results stated in these papers, which Shamir claims is incorrect. He emphasizes that he provides open code and step-by-step instructions for anyone to reproduce his original findings, directly challenging the accuracy of Patel and Desmond's reanalysis of his work.
Okay, that's a comprehensive rundown. So, pulling it all together, from Shamir's perspective, many of these studies suggesting pure randomness seem to have, let's say, methodological issues, whether it's sample size, human bias, excluding relevant features, using insensitive statistics, or potential errors in reproduction. He argues that when you look closely or reanalyze correctly, the evidence consistently points towards a non-random distribution of galaxy spins, especially becoming clearer at high redshifts like those seen by JWST, and with a pattern linked to the galactic poles.
That's the core of his argument, yes. He believes the superior data from JWST is sharpening the picture, confirming and strengthening these hints that have been around for decades, suggesting a genuine large-scale cosmic feature. It's a fascinating illustration of how science progresses through claim, counterclaim, refinement of methods, and the slow accumulation of evidence, often amidst considerable debate.
So let's assume for a moment. Let's entertain the possibility that Shamir is right, that this asymmetry is real and significant. What does this all truly mean for our understanding of the cosmos? Let's really explore the grand implications here. If this audacious hypothesis that our universe has a preferred spin, maybe it is rotating, maybe even connected to being inside a black hole, were to gain more robust evidence and eventually hold true, how would that fundamentally shake up cosmology?
Oh, it would be a revolution, a complete paradigm shift. First and foremost, as we discussed, a universe with a preferred direction of rotation would directly violate the isotropy assumption of the cosmological principle.
Meaning the universe isn't the same in all directions on large scales.
Exactly. And that principle is not just some minor detail. It's a foundational assumption built into the standard model of cosmology, often called lambda CDM. It underpins how we interpret the cosmic microwave background, how we model large-scale structure formation, how we calculate the universe's geometry and evolution. While the principle has faced some other observational challenges before, this galaxy spin asymmetry, if confirmed as a global property, would be a direct, large-scale empirical contradiction. It would force us to fundamentally rethink how our universe began and how it evolved.
Would throwing out isotropy help explain other big cosmic mysteries? Could it lead to breakthroughs where we're currently stuck?
Potentially, yes. That's one of the exciting possibilities. If our fundamental assumptions are wrong, it opens up entirely new avenues for research. It could potentially offer explanations for some of the most vexing, currently unresolved problems in cosmology.
Like dark energy. Or the Hubble tension?
Precisely. Take dark energy, this mysterious force causing the universe's expansion to accelerate. Our current model puts it in as a cosmological constant, lambda, but we have no deep understanding of what it is. Or the Hubble tension, this persistent disagreement between measurements of how fast the universe is expanding today versus predictions based on the early universe. Maybe a fundamentally rotating universe, or one embedded within a larger structure like a black hole, offers a completely different dynamical framework that could resolve these puzzles naturally, without needing separate, often ad hoc, explanations like dark energy or unknown measurement errors.
It's fascinating how challenging one assumption could potentially solve other unrelated problems. Now, I recall hearing about Kurt Gödel, the famous logician, and his idea of a spinning universe way back. How does that connect here?
Ah, yes, Gödel's universe. That's an excellent historical connection.
Yeah.
Back in 1949, Kurt Gödel, who was a close friend and colleague of Albert Einstein at Princeton, found an exact solution to Einstein's own equations of general relativity. And this solution described a universe that was inherently rotating.
So, Einstein's own theory allows for a spinning universe.
Mathematically, yes. Gödel's solution was perfectly valid within the framework of GR. And it had some really bizarre properties. Because of the rotation dragging space-time around, Gödel showed that his universe actually allowed for time travel into the past. You could follow a path through space-time and end up back before you started.
Time travel. Wow.
Yeah. Gödel apparently liked pointing this out to Einstein, partly to argue about the nature of time itself. While Gödel's specific rotating universe model doesn't match our observed universe, it wasn't expanding, for instance, it demonstrated mathematically that the concept of a rotating cosmos wasn't forbidden by our best theory of gravity. So the idea Shamir is exploring isn't completely out of left field theoretically. It has a fascinating historical precedent.
Okay, so it could impact fundamental principles, potentially solve mysteries like dark energy. Beyond just individual galaxy spins, would a rotating universe affect the bigger picture? Like how structures form?
Absolutely. It would have profound implications for the formation of cosmic structure as a whole. Our current models assume structure, like galaxy clusters, filaments, voids, grows from tiny quantum fluctuations in the early universe in a basically isotropic way. But if the universe has an overall spin, a preferred axis, that could imprint itself on how large-scale structures form and align. It might dictate preferred directions for galaxy cluster mergers or the orientation of the vast filaments of the cosmic web. It wouldn't just be about individual galaxy spins. It could be about the alignment and evolution of the entire cosmic structure.
And connecting back to the most speculative idea, if the universe is the interior of a black hole formed in some parent universe,
Then that immediately ties into ideas about the multiverse, the possibility that our universe is just one bubble among many. And as we established, black holes are expected to spin. So if our universe was born from or inside a spinning black hole, it would naturally inherit that spin. The observed galaxy asymmetry could then be seen as direct evidence supporting not only a rotating cosmos, but potentially this whole black hole cosmology and multiverse scenario. It connects a lot of speculative dots.
that is truly mind-bending. Our entire cosmos as a spinning structure within something even grander. Okay, let's pull back from the brink a little. These are huge ifs. What about alternative explanations for the observed asymmetry? Ways to explain the lopsided galaxy spins without needing a rotating universe or living inside a black hole. Surely scientists are exploring left radical options if the cosmological principle is to be saved.
Oh, absolutely. The principle of Occam's razor generally applies. Don't invoke radically new physics if a simpler explanation fits the data. And there are indeed alternative explanations being considered that don't require abandoning standard cosmology or resorting to such exotic ideas. They generally fall into two broad categories.
Okay, what's the first category?
The first category suggests the asymmetry isn't due to a global rotation of the universe, but rather reflects some kind of large-scale anisotropy or preferred direction within the universe's structure itself, the large-scale structure, or LSS.
So not spinning, but maybe. Lopsided. Or having a built-in direction.
Exactly. It suggests the fabric of the universe, the distribution of matter and energy on the very largest scales, might possess some kind of inherent cosmological scale axis or preferred direction. For instance, some theoretical models explore possibilities like an ellipsoidal universe, meaning the universe might be slightly stretched in one direction, like a football, rather than being perfectly spherical. Or maybe a dipole Big Bang, where the initial expansion wasn't perfectly uniform in all directions, leaving a large-scale gradient. Certain types of cosmic inflation might also naturally lead to such large-scale anisotropies.
So in these scenarios, the galaxy spins aren't responding to a universal rotation, but are aligning themselves with this pre-existing large-scale structure or direction.
That's the idea.
Yeah.
The large-scale distribution of galaxy rotation directions would be aligned perhaps subtly with this cosmic axis. The fact that the strongest asymmetry seems to be observed when looking towards the galactic poles from Earth could, in this view, just be a coincidence. Our solar system happens to be oriented in such a way that looking up or down aligns with this cosmic axis.
A cosmic coincidence. Could it also relate to how galaxies cluster?
Possibly. Some researchers suggest it might reflect a non-random, perhaps even fractal structure in the way galaxies cluster within the LSS on very large scales. This would also challenge the standard assumption that the distribution of galaxies in the LSS is perfectly random and uniform, but it wouldn't necessarily require the entire universe to be rotating.
Okay, so category 1, anisotropy in the large-scale structure itself. What's the second category of alternative explanations?
The second category is quite different. It proposes that the true distribution of galaxy spin directions out there in the universe is actually perfectly random and isotropic, consistent with the cosmological principle. But it only appears non-random to us here on Earth due to effects related to our own motion as observers and the physics of galaxy rotation itself. It's essentially an observer effect, or a selection bias.
An observer effect. So the asymmetry isn't real, it just looks that way from our perspective. How would that work? Like some kind of cosmic optical illusion?
Not quite an illusion, but more a subtle bias introduced by our own movement through the cosmos and how we detect light. The proposed mechanism hinges on the relative motion between the galaxies we're observing and ourselves, specifically the rotational velocity of those distant galaxies compared to the rotational velocity of our own solar system and Earth around the center of the Milky Way.
Okay, how does relative rotation create an apparent spin asymmetry?
It potentially comes down to the Doppler shift effect, but applied to brightness. Remember how light from receding objects is redshifted, stretched? Well, for a rotating galaxy, one side is moving towards us slightly, blue shifted, and the other side is moving away, red shifted, relative to the center. The idea is that due to the complex interplay of these motions relative to our motion around the Milky Way, galaxies that happen to be rotating in the opposite direction relative to the Milky Way's rotation might appear slightly brighter on average than galaxies rotating in the same direction.
Only brighter.
The exact physics is complex and debated, potentially involving how Doppler shifts affect the integrated light we receive or how efficiently we detect certain spectral features. But if it's true, even a slight brightness difference could create a selection bias. In deep surveys like JADI's, we're pushing the limits of detection. If one spin direction is systematically, even marginally brighter, we would naturally expect to detect slightly more of those galaxies, creating an apparent asymmetry in the counts.
Ah, okay, so we just see more of the slightly brighter ones, making it look like there are more of them overall.
That's the hypothesis. And interestingly, this observer effect model could also potentially explain the galactic pole connection. Calculations suggest that the difference in apparent brightness due to this relative rotation effect should be maximized when we are looking directly up or down out of the plane of the Milky Way, that is, towards the galactic poles. This is because that's the direction where the projection of our own orbital velocity around the galaxy is greatest relative to the distant galaxies. So the effect predicts the asymmetry should be strongest at the poles, which matches the empirical observations from DFLI and the JWST findings in GOODS versus the first deep field.
Okay, that sounds plausible, maybe connects the dots, but wait. Shamir found a huge asymmetry with JWST, nearly a 2/3, 1/3 split. Could a mild brightness difference really account for that big of an imbalance? That's almost a 50% difference in the numbers.
That is the major challenge for this observer effect explanation. Most astrophysicists agree that the direct effect of relative rotational velocities on apparent brightness, based on standard Doppler physics, is expected to be quite mild, as Shamir puts it. Probably not nearly enough on its own to explain the dramatic 50% difference in galaxy count seen in the JADES data, or even the smaller but still significant asymmetries seen in other surveys.
So the simple version of the observer effect doesn't seem strong enough.
Probably not. However, there's a fascinating counterpoint here, a twist. Shimmer notes that empirical observations actually measuring the brightness of galaxies spinning different ways in surveys like SDSS, PanSTARRS, and HST have shown that the observed difference in brightness is often larger than what's expected just from the simple Doppler effect caused by rotational velocities.
Wait, so galaxies spinning opposite ways do seem to have a bigger brightness difference than our standard theories predict.
Apparently, yes, according to some analyses of large datasets. This suggests there might be something more complex going on. Perhaps there's some mysterious physics of galaxy rotation itself that we don't fully understand, something that affects the light emitted by galaxies in a way that depends on their spin direction relative to us, beyond just the simple Doppler effect.
Mysterious physics of galaxy rotation. Well, what could that be related to?
Well, this ties into other long-standing puzzles in galaxy dynamics. We already know that the observed rotation speeds of stars and gas in galaxies are often much higher than expected based on the visible mass, stars, gas, dust alone. This is the primary evidence for dark matter.
Right, the idea that there's invisible matter providing extra gravity.
Exactly. But dark matter itself is still a hypothesis, its nature unknown. And there are alternative theories, like modified Newtonian dynamics, MOND, which propose changes to gravity itself on galactic scales to explain rotation curves without dark matter. These are all unresolved issues. So if the fundamental physics governing galaxy rotation is still not fully understood, maybe it does affect the emitted light, or how that light travels to us in unexpected ways that depend on spin.
And if galaxy rotation somehow affects the light more than we thought, could it even affect the redshift we measure?
That's the really intriguing extension of this idea. If there's some unknown physical process linking galaxy rotation to the properties of the light emitted, it's conceivable it could also subtly affect the light's wavelength, which is what we use to measure redshift. And if redshift
relies heavily on redshift measurements, might need rethinking.
Exactly. Hypothetically, alternative redshift models, ones where the observed redshift isn't just due to cosmic expansion and simple Doppler shift, but also includes some contribution related to galaxy rotation or other internal physics, could potentially offer explanations for many of the big cosmological puzzles we've talked about.
Like dark energy and the Hubble tension again.
Yes. Some proponents of these alternative models claim they can explain the apparent acceleration of the universe, dark energy, or the Hubble tension without invoking new substances or forces, simply by reinterpreting redshift data. They might also offer explanations for other anomalies, like the surprising number of very large, massive galaxies JWST is finding in the extremely early universe galaxies that seem too mature for their age, according to standard models, or even the existence of a few nearby stars, like the Methuselah star, HD 14283, whose estimated ages based on stellar evolution seem older than the currently accepted age of the universe itself.
So these are all real tensions, real observations that are genuinely challenging modern cosmology and pushing the boundaries.
They absolutely are, and they're triggering a whole range of potential solutions and explanations, many of which involve proposing entirely new physics or questioning fundamental assumptions. The galaxy spin asymmetry observation might just be another crucial piece of this complex puzzle. Regardless of whether the ultimate explanation is a rotating universe, an observer effect hiding deeper physics, or something else entirely, it forces us to scrutinize our foundations and consider possibilities we might have previously dismissed.
Okay, so to try and wrap up this deep dive then, we've journeyed through this really captivating, pretty audacious idea that our universe might be rotating, maybe even residing inside a black hole. An idea sparked initially by hints in older data, but really brought into sharp focus by these recent JWST observations, showing a puzzling, statistically significant asymmetry in galaxy spins, especially in the early universe and near the galactic poles.
And we've also seen how that initial observation, while statistically strong in the JWST data, is still far from being universally accepted as proof of a rotating cosmos. We explored how the author, Lior Shamir, vigorously defends his analysis and interpretation against critiques concerning methodology, statistics, and potential biases in other studies. And we touched upon the truly revolutionary implications if this hypothesis were eventually confirmed, challenging the fundamental cosmological principle itself.
But we also explored the alternatives. Maybe it's not rotation, but an anisotropy in the large-scale structure. Or maybe it's an observer effect, hinting at complex, poorly understood physics related to galaxy rotation and how we perceive light, which could also have profound implications.
Exactly. And the real value here, perhaps, isn't necessarily whether the universe is literally inside a black hole right now, but the value of asking these kinds of fundamental questions. These bold, speculative ideas, even if they ultimately turn out to be incorrect in their initial form, serve as incredibly useful foils. They force us, as scientists and thinkers, to constantly reassess the assumptions that underpin our models.
No theory should be considered sacred, right? Especially when new data comes along.
Precisely. No theory, no matter how successful or long-standing, should be above re-examination. We absolutely must continually test our foundational ideas against new, high-quality data, especially from instruments like JWST, that are opening entirely new windows onto the universe, particularly its earliest epochs.
And it's clear that modern cosmology still faces genuine, profound questions that we don't have definitive answers for yet. The true nature of dark matter and dark energy, the Hubble tension, the formation of those early massive galaxies. These are major unresolved issues.
They really are, and we simply don't know where the ultimate solutions may lie. They might come from completely unexpected directions.
So while we probably don't live inside a black hole in the simple sense, perhaps the research prompted by investigating that very bold, speculative idea might give us a surprising clue about dark energy or galaxy formation or something else entirely. It might push our understanding in unforeseen ways.
It very well could. And for those reasons alone, for pushing boundaries, for forcing critical reevaluation, for sparking creativity, these ideas are valuable. They are worth keeping around, worth exploring seriously, even if they don't pan out exactly as initially hypothesized. They compel us to think deeply and creatively about the cosmos and our place within it.
So here's something to ponder as you go about your day listening to this. If the universe does have a preferred direction of rotation, or if these galaxy spin asymmetries are indeed pointing to some fundamental, non-random property of the cosmos or our observations, what else might we be fundamentally misunderstanding? What other profound secrets are still lurking out there, waiting for JWST or perhaps even future telescopes we haven't even built yet to reveal? And maybe more personally, what does grappling with these possibilities mean for your understanding of our place in this vast, mysterious, and clearly still unfolding universe?